Welcome to Efiwe, excellence without stress.
Welcome guys to Efiwe, excellence without stress. And today we're going to be considering rates of chemical reaction. Now, why are we discussing this? Some reactions occur faster than some other ones. And basically, you'll find out that because of this, we'll need to understand how fast a reaction occurs with respect to another. If you consider a reaction between silver nitrate and hydrochloric acid, you find out that that reaction occurs almost immediately. But when you consider something like rusting of iron, it actually takes quite a while to happen. Zinc chloride, for instance, when it reacts with HCl, will produce ZnCl2 and hydrogen. And if we want to measure the rate, we can either measure with respect to the amount of zinc that is consumed or the amount of Zn chloride that is produced. Hence, rate of chemical reaction is simply the number of reactants converted or product formed per unit time. So we have that if we are dealing with the reactant, we'll say it's the amount of reactant over time. But if it's the product, we'll say the amount of product over time. So just have that in mind, that reaction rate is equals change in concentration of reactant or product all over time given. Let's look at this example. When 0.5 gram of calcium carbonate was added to excess dilute hydrochloric acid, carbon dioxide was evolved. The entire reaction took 5 minutes. What is the rate of reaction? So for the reaction to be completed, 0.5 grams had to be completely converted to carbon dioxide basically in that reaction. So how then do we solve this thing? Since they give us the reactant amount, we are going to use reactant divided by the time, and we have our answer. Now in most cases, your rate of reactions will be given in amount per time, and the unit of the time is usually in seconds. Hence, let's take note of this, that if we are giving rate and rate is equals amount over time, if you are giving your time in minutes, it's important to convert it to seconds if your rate is in gram per second. So we have 5 minutes. So if we are doing this, this is now going to be 0.1 gram per minute. But if this time was, the unit of the time is in seconds, we'll need to divide this 5 by 60, and by doing that we are going to now have that this is going to be rate equals 0.5 gram divided by, okay, so that will be times 60 all over 5. If you have this is going to still be 0.1, but this time times 60, and that's going to be 6 gram per second. So that's that basically about rate. You can try out the next question as your own example. Moving on. Collision theory is another aspect, and this is simply because for any reaction to occur, the particles must collide. Hence, collision theory assumes that there must be a collision between reactant particles for a chemical reaction to occur. Although there are many of such collisions, only a small fraction of them results in what we call effective collision. Now, a collision is said to be effective if that reaction eventually leads to the formation of a product. In a reaction system, particles move about different speeds as they possess different amounts of energy. For instance, if you have a higher energy, it's expected that you should run faster. If you have lower energy, it's expected that you should run slower. So that's the same thing with reactants and reactions. For a chemical reaction to occur, the colliding particles must possess a certain minimum amount of energy, and that minimum amount of energy is called its activation energy. In all chemical reactions, existing bonds in the reactant particles have to be broken first before new bonds can be formed to produce product particles. And with this said, you will find out that if you have not gotten to your activation energy, as we can see in this diagram, you will find out that it will be hard for this reactant to be converted to this product. So if this is the reactant and B is the product, for A to go through a process and then turn into the product, it must get to this activation energy before it turns into a product. With that said, we will move on to the next one. Now, reactions occur if the energy of the colliding particles is equal to or more than the activation energy. So if you have that the energy you possess is not up to that minimum requirement, you will not be able to be converted from a reactant to a product. Every reaction has its own activation energy. Now, reaction A, activation energy might be up to 1000, while that of a particular other one might be less than 1000. The point is this, that every reaction has different activation energies, and once you don't have up to the activation energy, that reaction cannot occur. A reaction with a low activation energy will take place spontaneously at low temperature. So the implication is that if the activation energy is lower, it occurs without increase in temperature above room temperature. But if you have a reaction with a very high activation energy, it would only take place if supplied with an external form of heat or light or electrical energy. So the higher the activation energy, the more requirements for that reaction to occur. But if the activation energy is low, it actually leads to a spontaneous reaction between substances. Now, exothermic and endothermic reactions. Both exothermic and endothermic reactions generally require an initial input of energy to overcome the activation energy barrier. Exothermic reactions, once started, may evolve enough energy to activate more reactant particles so that the reaction can proceed without any further external energy supply. Endothermic reactions have to be continually supplied with an external source of energy for the activating reactants, for activating the reactant particles as well as to form the product. So the point is this: if the reaction is exothermic, once it starts or becomes ignited, it begins to produce heat. Hence, other particles around will now be activated by the heat produced by that process. But in the case of endothermic process, it absorbs heat, which means that you will need to continually supply that particular reaction with heat for more products to be formed. Now, if we consider the diagram or the graph of an endothermic and exothermic process, what is the major difference here? Now, notice that in the case of an endothermic process, the heat of the product is higher than the heat of the reactant. So the energy, if you see the position of the product, this is the product, this is the product, this is the reactant. So the energy of the product is higher than the energy of the reactant, and because of that, you notice that when we have our enthalpy change is given as dH equals heat of product minus heat of reactant. Once the heat of product is greater than the heat of reactant, you will notice that enthalpy change will be positive, and that is what we see in this graph here. So if you look at the graph, you notice that the product is higher than the reactant, hence dH will be positive or greater than 0. On the other hand, for exothermic reaction, you have a negative enthalpy. Why? Because in an exothermic reaction, the heat of the reactant is greater than the heat of the product, and because of that, your dH will be negative. You can actually illustrate that with values. If, for instance, we have that the heat of product is 7 and heat of reactant is 5, you have +2. But on the other hand, if you have that the heat of product is 5 and the heat of reactant is 7, you have -2. So just take note. Now, when the heat of product is higher, endothermic process, but when the heat of reactant is higher, exothermic process. So you can use that to note how to identify your graphs basically. So if you look at a graph and you notice that inside that graph, the product is higher. Once product is higher, endothermic, but once reactant is higher, exothermic. Moving ahead. What then are the factors that affect rate of reactions? The first factor is the nature of reactants. Yes. Then we have the concentration or pressure of the reactants. Then we also have surface area of reactants, temperature, pressure, and then the presence of catalyst. Let's discuss this in details. Now, when a piece of iron is placed in dilute hydrochloric acid, there is a slow evolution of hydrogen gas. With a piece of zinc, hydrogen is evolved more rapidly, and with a piece of gold, there is no evidence of reaction. Thus, the rate of a chemical reaction is determined by the chemical nature of the reactant, as different substances have different energy content. So the implication is this, that the type of substance that is involved would actually determine if this reaction will occur faster. If a substance possesses higher energy and comes in, it makes it easier for it to get to the activation energy and then turn into a product. But for a substance that has a low energy content, it will first absorb energy to get to the activation energy, and then from the activation energy be converted to a product. With this said, we go to the next one, effects of concentration of reactants. Reactant particles will collide more often if they are crowded. Exactly. And as you are increasing collision, you are increasing the frequency of collision, you are increasing the chances of a reaction to occur. Remember that if there is no collision, there will be no reaction. That's the collision theory. Collision theory states that for a reaction to occur, particles must collide, which means if you increase the chances of particles colliding, you are increasing the chances of reactions. So have that in mind. An increase in the concentration of the reactant will result in a corresponding increase or decrease in effective collision of the reactant and hence affects the rate of reaction. Pressure affects the concentration of gaseous reactants. So basically, if you increase pressure, you basically bring them to become more compact, and when they are more compact, their chances of collision is increased. Let's consider the effect of surface area. Basically, when a dilute acid is added to marble chips and to powdered marble, we notice a marked difference in the rate of reaction. The acid reacts more vigorously and faster with powdered marble than with powdered chips. The powdered marble offers a greater area of contact with acid than the marble chips, so that more marble particles can react with the acid in a given time. If you consider this, you will notice that if you bring cube sugar and ground sugar and dissolve the two of them in water, the ground sugar dissolves faster. Why? It is already broken down, so it has more interaction with the water. So when you are increasing surface area, you are trying to break it down into a level or point where it has more contact. So the implication is that if you have a pebble of nail or iron fillings, you have let's say iron rod, you have iron granules or ground iron that is ground into pellets, and then powder. The one with the highest surface area is the one that is in powdery form. And if it has a high surface area, it means that you are increasing the opportunity it has to directly contact and react with substances, hence increasing the rate of reaction. But when it is together and more bulky, you will notice that before the reactants penetrate to get to the inner parts, it would actually reduce the rate of reaction. So increasing the rate of reaction is directly proportional to increasing the surface area. Now, how do you increase surface area? Grind it, break it down to smaller particles, and when you break it down to smaller particles, you are increasing the area of contact for those particles and the reactant, hence increasing the rate of reaction. What then do we have to say about this? The greater the surface area of reactants, the higher its rate of reaction. So for example, zinc dust burns more quickly in oxygen or chlorine than zinc granules. So as I said, the more powdery it is, the higher the rate of reaction. We know that reactions, we're talking about the effects of temperature now. We know that reactions are faster at higher temperature and slower at low temperature for endothermic reactions. Many reversible reactions, if left at ordinary temperature, will take years or even centuries to come to equilibrium. In general, the reaction rate doubles for each rise of 10 degrees Celsius. The reverse effect of cooling a reaction in order to slow it down is also true. The point is, generally speaking, as you increase temperature, rate of reactions should increase. So it's just like dissolution. For instance, you will notice that if you pour red oil into your soup when making soup, it doesn't dissolve fast, but when you heat it, the dissolution or rate of dissolution of the oil increases. And that's that basically, that when you increase temperature, the rate of reaction should increase. Then we talk about the effects of light. Some reactions are influenced by light. The implication is that these reactions, when light is present, would occur more readily. Take for instance a reaction between hydrogen and chlorine. Is basically negligible in the absence of light, moderate in daylight, and explosive in bright sunlight. So the implication is that the more the light, the more the rate of the reaction between hydrogen and chlorine. Such reactions are known as photochemical reactions. Other examples include the composition of hydrogen peroxide, the reaction between methane and chlorine, photosynthesis in plants, and the conversion of silver halides to gray metallic silver used in photography. So these are examples of reactions that are dependent on light. Hence, an increase in light would cause an increase in the rate of those reactions. Finally, we'll talk about the effects of catalyst. A catalyst is a substance which alters the rate of a reaction, but itself does not undergo any permanent change at the end of the reaction. In the preparation of oxygen by heating potassium trioxochlorate 5 in the presence of a small amount of the catalyst, manganese 4 oxide, only moderate heat is needed to decompose potassium trioxocarbonate 5. Why? There's a catalyst there. So once you have that you are trying to produce oxygen by breaking down potassium trioxocarbonate 5, once you have the manganese 4 oxide there, it catalyzes the reaction and makes it happen faster. And that's that basically. In the absence of the catalyst, potassium trioxochlorate 5 must be heated to a much higher temperature and for a longer time in order to obtain this similar result. The point is this: because of the presence of catalyst, it will make the potassium triacylchloride 5 salts to decompose faster. But if there are no catalysts, it decomposes slower. With that said, a positive catalyst usually acts by lowering the energy barrier of a chemical reaction. So just in case you are asked, how does a catalyst act? A positive catalyst especially, acts by lowering the energy barrier of a chemical reaction. Thus, in the presence of a catalyst, more reactant particles are able to react when they collide. So with this said, we have come to the end of this study. I hope that you have learned a lot. Thank you very much.